This is 8-53. I want to go over the details of this part of this problem in case this would become a test problem on the test tonight. Here you have 3 loads being applied out here, and they want to know what the stresses are going to be caused at A. And I'm going to talk a little bit about what's taking place at B. If you're given a problem like this, what you're going to have to do is look and see and go back to the centroid where your axes go through and determine what the moments are going to be first. So now this 100 pounds is going to cause this purple moment here. So that'd be 100 times 8, and that's right here. And that would give me my 800. I'll do that in purple here. And those are all inch pounds. That's going to be going this way. Now you got 80 here. That's a vertical. That's a y component. It has a it causes a torque, if you want to say it, or a moment around the x-axis as 80 times 3. It also creates a moment around the z-axis of 80 times 8. So I did that. 640 inch-pounds coming this way. You got 80 times 3 coming this way. Again, the 100 is only 8 inches away from the z. That's why I only get the 800. 8 times 100 has there's no other distance in another axis from this point. The 75, you got the 75 times 3. Now you would have to consider what's taking place there. That's also creating a moment, and I haven't drawn that in yet. It's creating a moment going back this way here. And it's going the other way. And that gives me what? 225. Okay? So what I would do in this case, I'd probably make this one negative and let this one remain positive. So again, first thing, just clarify all the moments, make sure you draw all those, and make sure you look at all different possibilities. Now if I look at A, I have 75 pounds coming out. That's going to cause a tension force here. That's just going to be a P over A type force. You have 80 pounds coming down here. That's going to create a shear force across here. You have 100 going to the right. That's going to also cause a shear force across here. So what I show here in this picture, this is with the cross section. If I look at A, I have 100 pounds coming across here causing shear. I have 80 pounds down here causing shear. All right, so now let's think about what's taking place regarding the moments. What you would have here, we'd have 240 inch-pounds, this red one. So it's going like this. So that's causing a torque at A, okay? So you have to try to consider that. But the only thing is you would get shear at the outer edge. So what we could do to find out the shear, would we just do T torque times R divided by the polar moment inertia, where R is the distance from here to here. We can find out what the torque is going to be. Regarding the moments, let's talk about this. You got 800 and you got 225. So you'd have to take the difference of that. 800 minus 225. You get 575. So I'm going to draw that. I'm going to draw that in purple. You'd get 575 going back around. Oops, do it in purple. Sorry. You could be going around this axis here, and that would be 575. Now here you got the blue, which is 640. Again, it's kind of hard to do this around it, but it's going back this way, and that's going to be 640. So think about all the possibilities you were trying to find out what the stress with A would be. This moment here cannot create a stress at A because you have no C distance away, right? Because the moment is rotating around here. My C distance has got to go this way. So I wouldn't even have to worry about that. If I was going to find the stress at A, then what I would do, I'd take the 640 times the distance from here would be C, divided by the whole entire moment inertia. Okay, now since this blue would be causing tension up here, I would also have to come back and say plus P over A, 75 divided by the entire cross-sectional area. I'd add those two together. That's going to give me the stress at A. Now let's think about what I would do regarding B. if I was going to find the stress at B, and let's talk about just tension, well, I would have the P over A, the 75 divided by the entire cross-sectional area. But now when I do my moments, I ignore the B. I ignore the 640 because this cannot create any bending stress at B because there's no C value here. What I would do here, I'd have to consider the 575. So it'd be 575 times the distance from here to here divided by the moment inertia. Okay? Now the thing about that one would be, this would be causing, if you think about it, this would be causing compression at B because it's rotating it back this way. So I'd make maybe that one be negative and then subtract the 75 divided by the area, and that would give me the stress at B, and that would give me my combination of bending stress and tension. Alright, now we talked about torque. If I'm going to do the torque equation, it's going to be TR over J, and A and B had had the same shear stress as a result of the torque being applied. Now the torque in this case is going to be right here, 240. That's what's causing the torque, inch-pounds. So I'd take 240 times the distance r. The distance is going to be from here to here, or from here to here. It's going to be the same value divided by the polar moment inertia, and that's going to be the same. So I could get my torque stress. Now the only thing is I have to consider is my shear stress. I got shear 80 coming down here. This 80 could not create any shear stress at A because my Q value is going to be 0. It would create stress anywhere up through here except for at A. If I was going to find my shear stress, I'd have to consider my 100, and my Q value here would be, let me call it a different color. I'll do it in yellow or something like that. I'd have to consider all this area as my Q if I'm trying to find out what the shear stress at A would be as a result of the 100 pound. Now if I was going to do at B, I would consider the 80 coming across. The 100 would not create any shear stress at B. If I was going to find out what a B would be, I'd have to find out what all this area would be. That would tell me what the shear stress across here would be. All right, so again, it's a very complex problem, but you have to consider everything if you end up getting a three-dimensional, because these forces cause all kinds of issues. They cause moments, they cause shears, and they cause torques. Okay?